Now in this section we're going to take a look at inequalities, which roughly speaking are just comparisons between two quantities. So I want to start by just reminding you about some notation. If I draw a capital R, this is almost like a capital R. It's called a blackboard R. You can see I've got a double line there. But other than that, it looks just like a capital R, right? This stands for the set of all real numbers, which includes just about every number you've ever been exposed to. And you can sketch them in a picture by drawing what's called the number line, which I'll draw right now. So I just draw, typically you'll do a horizontal line, although there's no reason it needs to be horizontal. I'll just draw an arrow on either end to indicate that it goes on forever in both directions. And then I can pick certain points on this line and associate them with certain numbers. How about I call that -2, this will be -1, this will be 0, 1, 2, and since I've got room for it, I'll do 3 here as well. But note that everything else is included as well, even if I don't draw the number, right? So for example, I haven't drawn anything in between 0 and 1, but say the number 1/2, which would be right around here. It's not drawn exactly, but it's somewhere around there. That would be a half. What about the number pi, the special number pi? That would be a little bit bigger than 3, right? And I'll write it like that. This is just a reminder. This is the symbol for pi. It's approximately equal to 3.14. Then there's also other irrational numbers like the square root of 2. That would look like it's about 1.4 something. So I'll write that down here. It's approximately 1.41. It might actually be 1.42. I can't remember, but it doesn't matter, right? It's close to 1.4. It's somewhere in between 1 and 2. The point I'm trying to make is that the real numbers, the set of all real numbers, it includes everything. It includes 0, all your negative numbers, all your positive numbers, and all the fractions, rational numbers, but also irrational numbers. Okay, so all those numbers are included in the set of all real numbers. And notice that I drew these labels below the number line, and then I drew these other labels above the number line. There's no rhyme or reason to that. That's just a matter of choice. Now, I shouldn't say there's no rhyme or reason. There was a reason for that choice. And the reason was, if I had drawn 1/2 down, but let's imagine I drew these all down below. Gets a little tough to read, doesn't it? So that was my reasoning. I just did the whole numbers, the integers, which are down here, the whole numbers, including 0 and the positives and negatives. I drew those down because they were nice and evenly spaced out. But then the extra couple of numbers that I wanted to add, I chose to label those above the number line. But the point here is that you can do either or. But pick one and have a reason for it, basically, right? Okay, so that's just a reminder on the set of all real numbers. Now let's get to the text proper here. So here we're going to start with the assumption that we've got two real numbers, a and b. So this symbol here, this symbol here, that just means is an element of or belongs to. So if I say something like let a and b be elements of R, that's what this is really saying. I just want to say let a and b be two real numbers, okay? And I'm trying to stay as general as possible. That's why I'm using letters. But we're going to actually make an additional assumption and assume that a is less than b. That's what this notation means. Just I'll give you a reminder as well. This means a is less than b. So in terms of the number line, that would mean a would be over here maybe, like in this direction, and b would be over to the right. If I were to plot just the numbers a and b on the number line, then a would be to the left, which we'll do, and we'll do that in just a moment. But first I want to tell you something else, which is what the open interval from a to b is. Now, really, if I back up just a moment, what you often want to do is you want to describe regions of numbers. Like you might make two, don't write this down, I'm just going to erase this momentarily. But if I wanted to say chop the number line there, and I want to describe all the numbers in between and nothing else, that's where intervals will become useful. So with that in mind, let's describe what the open interval AB is. So here's the notation that you would use. You just read that out loud as the open interval from A to B. And you can see it's got round brackets, and then the numbers A and B are just listed with a comma in between them, right? So what that notation means is, let's read this carefully. It consists of all the real numbers, and x is going to be a temporary placeholder for such a real number. So all the possible values that you could plug in for the variable x that would make the following inequality true. And here's the inequality. So the inequality is that there's actually two inequalities combined into one here. First of all, a is less than x, but also x is less than b. This is just two inequalities written together to be concise, right? So this is just saying that a is somewhere in between a and b, and in a strict fashion, in the sense that it's neither equal to a itself, nor is it equal to b itself. It's got to be something strictly between those two values. Okay, and you can sketch this on the number line, which is quite useful. It's a lot easier to think about if you actually sketch it on the number line. So let's do that now. And the nice thing is when you're drawing a number line, you don't have to label everything, right? You can just label what you need. So in this case, we're just talking about the open interval between a to b. So I can just label a and b and nothing else. And notice I've got a appearing on the left because of this assumption. A was less than b. Okay, and then b is over on the right because it's the larger of the two quantities. Okay, so this open interval from a to b, this is all the points in between. So what I'll do typically is I'll shade them. I'll just make the line a bit thicker there to indicate that I want to include all of those points. Now I don't want to stop here because it's unclear at this point whether or not the endpoints a and b are included. Now I mentioned here that they're not included, but if I'm just going by the picture, I want to make that clear. So what you'll do typically is you'll just draw a big empty dot on either end. So notice I've just got a nice big dot, but it's an empty circle. That's what indicates to the reader that those endpoints are not included. Okay, so all those points in between, put them together into a set, and this is the open interval from a to b. All right, well, what if I do want to include the endpoints a and b, right? Because sometimes you might want to. And in that case, well, then you can use what's called the closed interval. The closed interval from a to b. And notice there's a difference in notation here, right? If you take a look, you can see that there are square brackets. That's the only difference in notation, but everything else is the same. It's the same as what we had up here, right? The only difference is that the brackets have changed to being square. So that is a meaningful change. As soon as you see that change, that means you're talking about a closed interval. And then you're going to actually use a similar sort of inequality as the one we used here, except you're going to relax the restriction that x is not allowed to be equal to a or b. So the way you would write that as an inequality is you'd say that a has got to be less than or equal to x, and then x has got to be less than or equal to b. Okay, so x, in other words, x is somewhere in between a and b, or possibly equal to a, or possibly equal to b. You're allowing for all of those possibilities. And the way you sketch it on the number line is almost identical. In fact, I could have copied and pasted it here, but it doesn't take very long to draw, so let's just practice drawing it again. So if I want to label all the points between a and b, I still want to include these, because intervals are that's what intervals are still for. Closed or open, they're really meant for describing all of the points in between two particularly chosen endpoints. But since we've got a closed interval, instead of getting an open circle on the end, we're going to get a solid circle on the end. So notice I've got just the only difference is that the circle's shaded in. Okay, and that just means visually, if I didn't have any of this shown to me and I just saw this in a picture, I know that whoever drew that diagram, they're trying to describe all the numbers that fall between a and b, or possibly are equal to a or b themselves. Okay, so that's an open interval and a closed interval. What if you want it to be even more specific? What if I want to include one of the endpoints, but not the other? So let's say I wanted to include a, but I didn't want to include b. Well, you have an option for that as well, and those are called half open intervals. Okay, so rather than going through every single case, what we're going to do is just look. You can see them listed in a table below. So the first two, let me switch to a highlighter here. So the first two, those are the ones we just discussed, right? You've got the open interval a to b on the top row, and then you've got the second row has the closed interval a to b. Those are the ones we just went through in detail. Let's take a look at the third one. So what's happening here? Well, now first of all, look over here. You've got a square bracket on the b, but a round bracket on the a. That's how you can specify just including one of the endpoints if you want. So that's called a half open interval from a to b. It does include b, but it doesn't include a, and you can see the inequality reflects that, right? A has to be less than x strictly, but a has to be less than x in a strict fashion, but then x has to be less than or equal to b in a non-strict fashion. If you're allowing for equality, it's called a non-strict inequality. Okay, so and in the picture you can see B is shaded and A is not. Now, what about the next one? It's the exact opposite situation here, right? In this case, the square bracket's on the A, so A is actually included, which you can see here. The round bracket's on the B, so B is not included. And then again, the inequality reflects the fact that that it's strict on the upper endpoint. It doesn't include B, but it's non-strict on the lower endpoint, and then it does include A. Okay. What about the next one? This is new. Notice that the B is not there anymore. Nobody's put a B as the upper endpoint. It's still got a round bracket, but there's just this infinity symbol that you may recognize. Well, if you see an infinity symbol as one of the endpoints, really what you're saying is that there's no endpoint, right? It's kind of like when someone says the only rule is that there is no rules, right? It's kind of one of those goofy sayings, but that's kind of what's happening here. There is no upper bound, so we write the infinity symbol in place of the upper bound. So if there's no upper bound, then the shading just goes on indefinitely to the right. So, and you can see that, right? You got it, the lower endpoint is still A, but then instead of having an upper endpoint, the line just keeps getting shaded onward and onward to the right, and then the arrow is even made bold, right? So that just means the interval of points just stretches on forever in that direction. And you can do the same thing. I'll just jump ahead down here. You can do the same thing if you don't want to include a lower endpoint. Well, then you just replace the lower endpoint. Or instead of writing a lower endpoint, just write the negative infinity. That just means that the interval stretches on forever in the negative direction, and that's reflected in the always think of the pictures. The pictures make it clear, right? In the picture, you can see that the interval just stretches on forever to the left, so there's no lower bound, but there is still an upper bound, and that upper bound is labeled as B. And since there's notice that back to here, since there's a round bracket around the B, then you don't actually include B. So those are called uh, still called open intervals because they don't include their boundaries, but they're infinite intervals, right? What if you want to include the boundary B? Well, then you could just use a square bracket around B, and then it would include B. And in the first case, when we had the interval stretching infinitely far to the right, if we wanted to include the left endpoint A, again, we would just use a square bracket on the A to indicate that we want to include that point. Now, the only exception here is you never use square brackets on the infinity or the negative infinity. And the reason for that is that these are sets of real numbers, right? Intervals contain only real numbers. And infinity, as much as the concept is convenient, it's nice to have a little symbol that represents the concept infinity. That's just an idea. It's not a number, right? Infinity is a concept, not a number. So you'll never actually include infinity in your interval. Okay, so that's intervals for you.